Hi, in this lecture we are going to discuss how we rebalance an AA tree to maintain the depth small. After you insert an element into an AA tree, you have to rebalance or restructure it. The rule of thumb that we're going to follow when rebalancing is the following. First, we're going to make sure that only left-right edges are within nodes of the same level. Okay? If that doesn't happen, we are going to call a function called Skew. After that, we're going to worry about paths which are too long within the same level. What the skew operation does is the following. Skew on node X checks if node X has a left child with the same level. This is not allowed. So if that's the case, it's simply going to call rotate right at X. Okay, so you're going to rotate right at X, and that left child will just become the parent of X. It's gonna fix the problem. Split is another operation. It's gonna check if the level of the right child of X, so from X you go right child and right child, you check at this level, checks if that is the same as the level of X. Okay, this thing again is not allowed because we only allow a single left-right edge in the same level. If so, then what you do? Well, you're gonna pick the right child of X, okay, and you're gonna increase its level. So you're going to bring it up. If you have X, right child, and right child, you're going to bring up the right child of X, and then you're going to rotate left at X. So let's see these operations in action. If you want to insert an element K in AA tree, first you insert K as in a binary search tree, okay, just normally. And then you travel back from, you start from the node that you just inserted. You travel back to the root, following, say, parent pointers, and you just call skew and split on each node. Okay? So one way of doing this is following in slightly more detail. After you insert, you know that the new node is in the position num nodes -1. Okay, this is just in our array notation because num nodes is the number of nodes in the tree. So the new node is the last in the array. So this -1 is just because if the tree only has one node, okay, it's in the entry index 0 in the array, but the number of nodes is 1. So you do 1 - 1 to get 0. Okay, that's all that this thing is. And then you continue as long as X is different from null. You call skew on X, you call split on X, and you move to the parent of X. Let's see this in action. Here is an AA tree, okay? And here is what happens when you insert 6. Okay, when you insert 6, what do? You first search for 6. So you start here, you go here, you go here, you go here, you go here. Then 7 does not have a left child, so you just put 6 here. This is what happens when you insert. Okay, and then you travel back and you call skew and split. Okay, you travel back, so you go to 7. Okay, so 7 now has a right-left edge in the same level. This thing is not allowed, so I'm going to call it, so skew is going to fix it. It's going to do a right rotation at 7. It's going to move 7 right clockwise here and bring 6 up. This is what happens here. Now here the situation is fixed. This edge is left to right. This is allowed, but if you go up at 5, you have 2 in a row, which is not allowed. So split is going to fix that. what split does, remember, it's gonna increase the level of this middle node, and it's gonna do a left rotation F5, which is gonna bring 5 here and make it a left child of 6. Okay, so after you do this, you have this 6 now has level 2, and 5 is the left child of 6. Okay, and this has fixed the operation up to this point. You keep going up. You have an 8 here, which has a right-left edge to 6. So this thing is not allowed. So Skew is going to fix that. It's going to do a right rotation at 8. It's going to move 8 clockwise. 6 now is going to become the parent of 8. As you remember, when you do this rotation, the right child of 6 is going to go to 8 as left child, and that's what happens here, okay? So 6 went up, 8 is here, and the left child of 8 is 7. You keep going up, there's no problem, and you're done. Okay? You have maintained that this tree is an AA tree after an addition. Deletion is more complicated, but really the big saving of AA tree is that I'm still going to be able to present you a complete description of deletion, while for the other trees this thing gets very complicated. For deletion we need one more operation. It's called decrease level x, and it behaves as follows. If x has a child which is 2 levels below x, okay, that's not allowed. So we're going to decrease the level of x by 1. Okay, and if it happens that the right child of x also had the same level of x, then we're also going to decrease the level of that right child by 1. Okay. So it's a case in which you have to bring down nodes. Okay, you do it if there is too big of a jump between a node and its child, and if this node happen to have a right child with the same level, then you also bring down that. Okay, and now just with this I can describe to you the delete operation. And again, this thing is really a big saving over other data structures in which this thing has really a large number of cases, and it becomes quite complicated to explain. Okay, so let me describe how delete works, and we're first going to do it in a case in which x is a leaf. I'm going to explain how you delete a leaf node. Okay, and then I'm going to explain how you delete any node in the tree. There is like a generic trick that you can apply to any tree to go from a leaf to any node. So let's just assume that x is a leaf now. So first you're going to delete x. Okay, so you're just going to remove that node, and then again you're going to follow the path from x to the root, and at each node that you encounter, you're just going to call a bunch of times these operations. Okay, you're going to call decrease level. We just explained, and you're going to call a bunch of skews and a bunch of splits. Okay, so you're going to call skew on y, on the right child of y, and on the right child of the right child of y, and also split on y and on the right child of y. Okay, why exactly you just need this tree? 3 calls to skew and not 4. Okay, so you can sit down and analyze the cases. It was shown that 3 is enough. Okay, and it was also shown that 2 splits is enough. If you just call skew y and split y, this thing is not going to be enough. There are counterexamples. Here is an example of deletion. Here is an AA tree. Okay, and we're going to delete 1. Okay, so after we delete, then we go back to the root. The first node that we encounter is 2. and we call decrease level. Okay, so for the deletion now it's more useful to think that the leaves have children which are nodes level 0. Okay, so when you do this level 2, you find that level 2 has a child level 0. Okay, this is not allowed, right? So 2 has to decrease level. So 2 goes to level 1 here and has a right child 3, and then again you go to 4. Now 4 has the left child level 2. It's a jump too big, so you have to decrease the level of 4. Okay, and because 4 has a right child which is 10, you also have at the same level, you also have to decrease the level of 10. So both 4 and 10 will now have level 2. Okay, and then now you call the skews and the splits on 4. The first thing that you do is call this the skews. Okay, and in this picture from here to here, there's actually 2 skews which are taking place. Okay, the first skew is that you look at this edge is fine, but you also call skew on the right child of 4, which is 10, which has this edge here. This thing here is not good. Okay, is a right left edge on the same level, so you have to perform a right rotation at 10, right? So that's gonna bring 6 here, 10 goes down, and the left child of 10 will be 8. So the important thing is that the left child of 10 will be 8, so you get an edge 8 from 10 to 8, right left edge, and this again is a case which is not good. That's why you call a skew again, and you perform another right rotation at 10. That's gonna bring 8 up, and the right child of 8 will be a left child of 10. So you get the situation here after you're done with the skews. Now you start calling the splits. Okay, so the first split, you see that 4 has the right child of 4. The right child of the right child of 4 is on the same level. This thing is not allowed. So what you do, you increase the level of 6. So 6 now will have level 3. Okay, and then you perform a rotation, left rotation at 4. Okay, so 4 goes here and becomes the left child of 6, and now 6 will now have the right child 8, which again has 10. This thing again is not allowed, so that's why you call a split again, and the effect of that is that you're taking 10, you're going to raise it up, and you're going to do a left rotation at 8. You're going to get this picture here. So even here there are 2 splits being done, 2 skews to go from here to here, and 2 splits to go from here to here. This thing is complicated, but you're seeing what happens in pretty much complete detail, which is really a benefit of AA trees. So we just discussed how you can delete a leaf, and I just want to conclude with some observations on how you delete a node which is not a leaf. And this thing is a generic trick that you do for any tree data structure like AVL, red and black, and so on. So what to do if you want to delete X, which is not a leaf, okay? You're going to find the smallest leaf which is bigger than the key of X. You're going to swap it with X. You're going to remove that cliff. Okay. Okay. The way in which you find that cliff, which is just bigger than X dot key, you're going to perform the search, and whenever you find the node X, you're going to go say always right. Okay. So it's the same thing as searching for something which is slightly bigger than x.key. Say it's x.key plus epsilon. And the observation is that if you swap these two, you will not destroy the three properties. Okay. So if you have a node and then you find the leaf which is it's the smallest leaf that's bigger than that node, if you swap those two, you will not destroy the three properties. Here is a concrete example. Here is a tree. Let's say you want to delete one in this tree, which happens to be the root. Okay. If I want to delete it, first I'm going to find the leaf, the smallest leaf, which is bigger than 1. Okay. So I'm going to go right here at the left. I find these two. This is the smallest leaf, which is bigger than 1. I'm going to swap it with 1. So I get this tree here. Okay. So I swapped 1 and 2. And now if I now I'm going to remove 1, which is the leaf, with the process which I just described, and this is going to be a beautiful tree, you know, with the correct properties. So okay, after I erase 1, it's going to be a binary search tree. Great. I want to conclude with a couple of remarks. So the first remark is about the memory implementation. For when you add nodes, remove nodes, you could use something fancy like, you know, in C you have new malloc, in Java something like free and dispose, I think. And so on. If you do this, you rely on the operating system to decide where you should store your nodes in the memory of your machine. And this, in some cases, may give you some memory segmentation. You may also have delays and so on. Okay. If you want to keep things completely under your control and really understand what is going on, you can use our array representation. And then there is the issue, you know, if you want to remove a node, how you do that from the middle of the array. Okay, and it is possible to implement the tree using arrays in a way that at any point in time, if you have n elements in the tree, those will take the elements only from 1 to n in the array. Okay, so even if I have an array with n elements, and you remove, you know, something in the middle, you can modify the array to just occupy the first n-1 positions. And to accomplish this, when you remove a node with index I, you're just gonna swap this node with the last one in the array. Okay, just the place in the array in which the information on that node is located, and then you remove the last thing, and then you can just reduce the array length. Okay, and you can use the pointers to make the updates. The final remark for today is this. So the summary is that we have seen how you can support a search, insert, and delete in time order of log n for arbitrary keys. Okay, not just for small numbers. And the space that we use for this is order of n. Okay, why is order of n? Well, we have to keep this tree. We have to keep all the keys, that just n. But in fact, for every node, you also have to store the pointers. Okay, pointers to the children and pointers to the parent. Okay, so that gives you maybe like 4n space. And this is a very fundamental data structure, so it's natural to ask if you could do smaller space. In particular, it is kind of annoying that for each key element, you have to use 3 other items just to have pointers. So there is really, you know, the the overhead per key is just 3. So you pay 3 pointers, 3 extra pointers per key element. Okay, so If you want to store 1 gigabyte of items, now you get just 3 gigabytes just for the pointers for that. So can we get rid of the pointers and achieve space n? And surprisingly, this is possible. Okay, we're not gonna see how to do it, but there is a nice paper, fairly recent actually, relatively speaking, that shows how you can do that. Okay, so they show how you can support a search, insert, and delete in logarithmic time using just space n. Okay, we will see other data structures, heaps, which support some of these operations in space n, but they can support all the three.